Hi, my name is Mason Bell, and I'm here with Phaedra Curlin and Maddie Muniz from the University of Colorado Boulder. We're presenting our lab's work to support the construction of lunar infrastructure, leveraging low-latency virtual and augmented reality teleoperation. We're motivated by NASA's goals for a sustained lunar presence through the creation of the Lunar Gateway and the deployment of various lunar surface assets. Our work directly aims to support Farside, a concept mission calling for a strong collaboration between humans and robots to construct a low radio frequency array on the lunar far side. As we unlock the ability for low latency control over surface assets, we are led to consider the methods used during human-robot interaction. Our lab has focused in on the point of autonomous robotic failure, calling for teleoperator support. We suggest a risk-free failure response method in the form of our virtual recovery sandbox, a virtual environment representative of the robot's current state for operator solution development. This method aims to create a reliable real-time failure response as opposed to traditional methods such as the Mars Yard, a physical hardware duplicate of the Mars rover used to recreate failure states down on Earth. Our robotic system, Armstrong, provides a platform to implement and assess various facets of low-latency teleoperation. A 6-degree of freedom robotic arm allows us to assess experiment-based assembly tasks. The Z-Mini stereo camera supports operator telepresence through a real-time stream to a head-mounted display. This allows for an immersive control perspective viewed through the eyes of the rover. Servo motors supporting the camera allow for the replication of operator head movements, further strengthening the immersion and operator control ability during remote teleoperation. This platform is an ideal candidate for situations where the operator cannot be placed locally with the robot, as may be the case when controlling lunar robotics from the gateway. The Z-Mini stereo camera also supports the creation of virtual environments through real-time 3D scans. Using a high-fidelity model of the Armstrong rover, we've developed a virtual space representative of the robot's current state and environment. We call this our virtual recovery sandbox. The main objective of the sandbox is to provide a risk-free failure assessment and solution development environment accessible in real time when the operator cannot be placed locally with the robot. Within this space, the operator has access to the same control interface used when operating the physical robot. The virtual rover leverages the same software used to operate the physical rover, allowing for a transferable operation experience between both the physical and virtual platforms. The egocentric control perspective is used to simulate physical robot telepresence within the sandbox. Operators may control the rover to develop solutions to the robotic failure. Additionally, within the sandbox, we've provided the ability to access the exocentric viewpoint, a third-person observation mode allowing for the operator to gain additional information about the failure and environment. This perspective is enabled through the use of onboard robot cameras constantly scanning its environment. Exocentric observation provides a unique perspective that would not be available during remote operation of a physical platform. To prove solutions developed in the virtual recovery sandbox are effective during physical teleoperation, we've developed a baseline experiment testing the success of operator recovery from a robotic failure state. Half of our participants will have access to the virtual recovery sandbox prior to taking over control of the physical rover, allowing them time to develop solutions to the failure state. The other half will take over control of the robot without time in a risk-free environment to formulate a recovery plan. Successes and failures will be noted during the physical teleoperation stage to prove whether or not the solutions developed virtually truly provided benefit over those who were not given the chance. Our failure state will be representative of a possible event during the deployment of the Farside radio array. Operators will need to realign small antenna modules, simulating the alignment of polarization axes of deployed dipole antennas on the lunar surface. With COVID holding us back from in-person experiments, we've had plenty of time to iterate on and improve our virtual recovery sandbox. We are excited to see whether or not a virtual simulation can truly provide the information and operation experience for teleoperators to successfully recover from robotic failures. If so, this platform opens the door for many other remote operator experiences during the deployment of lunar infrastructure. Thank you.